today I'm going to move into a new area. They call Eigen Values and Eigen Vectors. Okay? This is only for square matrix, like n by n matrix. On this slide, I just, it's one diagram. You know what the function is, right? Function is, in a way, is mapping from this domain to whatever the range, from one space to another space. This might be same dimension, or may not be same, or maybe same dimension, may not be. So in the case of square matrix, so this is function, right? So when you fx is a function. So ax is b is actually is function in a way. This is Coulomb space here, then move there. What space of this? This is row space, right? Or you can say this is domain, or this range. This is the terms you are using in functions. So ax is b. So x is vector, right? Also b is also vector. Okay? So here we are starting special vectors. When you apply a, so vector b is the same direction as vector x. Okay? Size may vary. Like many cases when you apply a to vector x, the direction of b might be different. But in this case, we are starting special vector. When you apply a to vector x, then they have same direction, like b is same as b. So that's what we call eigenvector. Also, as a scale, that's we call eigenvalues. So it has nice properties. So that's why we are studying that area. So test terms like when you apply x for on eigenvector a, then there's such a scaling lambda x. So lambda we call eigenvalue. Okay? So how can I find this one? It's when you manipulate, like when you move lambda x left side, then you can say ax minus lambda x, right? Then lambda x you can represent as lambda and I. So I is identity matrix, right? So what's this? A minus lambda I, x and 0. What's the space or x which satisfies this condition? Kimiju? What's this? Null space of a minus lambda I, right? So when you apply a minus lambda I, then it becomes 0, right? So x should belong to null space of a minus lambda I, right? Yeah, let me show some examples. In the case of identity matrix, it's identity matrix, right? When you multiply x, it's always is the same x come out, right? So in that case, what's the eigenvalue, 정민영? 모르겠다. 박호중, what's the eigenvalue? 1, right? That's by definition, right? Then what's the eigenvectors? No. What's the eigenvectors? Because basically what I'm saying is AX is lambda x. But this one only for some x, not for all some vector x. We call them as then for given lambda, this is eigenvalue. Some vector, we call them eigenvector. Okay? So basically Ix is just x, right? This is 1 times x, right? This is true for every vector, right? So in this case, eigenvector is every vector. Okay, this is a special case. This is a second example. It's a null space, like in the null space, let's say AX, right? What's a null space? When you pick one vector from null space, any vector, then you apply A, what's the result? 0, right? It's 0 vector, right? So whatever this belongs to null space, then this is 0, right? It means lambda is 0, right? So eigenvectors is every vector in this null space. Okay? We learned about projection, right? This is space. Yeah, we are projecting B, vector B, to this space. Once you project, it becomes PB, right? What happens when you project again? Like vector B here, once you project, then it becomes PB, right? It means what happens when you project twice? Yeah, 2 times. Basically, I'm asking here P. Once you apply, then I know this becomes whatever P, right? What happens when you apply again to P, whatever, that means P twice B. What's this for the projection? Still P, right? Still P, right? So because when you're flying on the airplane, then what's the closest point? Then okay, it's surface, right? Then when you ask a question again, you are already on surface, right? So in this case, and then the next question is, for projection matrix, lambda equal 1, is this eigenvalue or not? 박한솔, is this eigenvalue or not for projection matrix? Look at this diagram. For every vector on this plane, when you apply P, whatever P, it's the same, right? That's what we discussed. If B is not on this plane, once you project, it becomes PB, right? You're already there, right? Then you apply again, P, the same. So you can pick any vector you have V on this plane already. Then you apply P, basically P, V, still is V, right? So it means, okay, this is legal eigenvalue. Then what's the eigenvector? then whatever vectors are on the plane, those eigenvectors. Okay? So basically, for any vector on the plane already, when you apply this P, then still the same vector. So eigenvalues 1, then all vectors in the plane is eigenvectors. How about this plane, right? This plane. We understand, okay, whatever vectors in this plane, already in the plane, when you apply, same, right? What about these vectors which is perpendicular to this one? Whatever this another vector, let's say W. When you apply projection to W, what's the value? 0, right? So in that case, okay, lambda 0 is also eigenvalue, then eigenvectors are perpendicular to this plane. Okay? So in the case of projection, lambda 1 is eigenvalues, then eigenvectors are the whatever vectors on the plane, and lambda 0 is also eigenvalues. Then all vectors to the perpendicular is eigenvector. This is another vector. I say permutation. 현상원, what's the permutation? Permutation, like exchanging row. Okay, this is A, O1, and 1, 0. This is a 2 by 2. You are changing row, just row 2 becomes row 1, row 1 becomes row 2, right? So then you have AB. When you multiply O1, 1, 0, what's the value here? BA, right? So you are actually just exchange rows. Okay? From this, can you find any eigenvalue? 김영진. So we have matrix here, right? So we try to find the eigenvalues. So how can you find the eigenvalues? Eigenvalue means like A, whatever x, right? For whatever eigenvalue. This should be lambda I. 4 eigenvectors, right? So when you remove this means Ax minus lambda I ought to be 0, right? So this can be written again. This is lambda. I'm sorry. This is x. It's lambda I. X should be 0, right? What's the determinant of this one for eigenvectors? 0, right? So it means A minus lambda I should be 0, right? So how can you compute A minus lambda I? So basically it means whatever this 1, 0, 1, 0, or 0, 1, 0, 1 is like minus lambda, 1, 1, minus lambda, right? So this one is lambda, what? Square minus 1, right? So lambda is 2 base, what? Okay? So Basically, this is the way you can find the lambda. Or sometimes by observing that, by using certain logic, you can find, right? But in general, you have to use this polynomial. Then you are able to compute this lambda. Okay? Then how can you find eigenvector? Like in the case, let's say, you say this is, in the case of lambda 1, okay, in the case of lambda 1, I try to find eigenvector. So how can you find the eigenvector in the case of Here we assumed, okay, this A, right? Whatever x should be 1x, right? In the case lambda 1, right? In the case lambda minus 1, then it should be x is minus x, right? So here was 0, 1, 1, 0. What's the x? Can you guess, just based on that? Oh, it seems to be okay. 1, 1 seems to be satisfying there, right? So 1, 1, then this is the same. So how about this? Like 0, 1, 1, 0. What's the x which satisfies that? This is more or less, look, you can say even or 1 or minus 1. But also when you multiply constant c, this one also satisfies the condition, right? Let's say it can be, okay, 2 is fine, right? Right? Also even here, okay, so 1 minus 1 is also okay, right? So when you have eigenvector, when you multiply whatever constant, coefficient, then also satisfy it, right? So that's the way I computed eigenvalues and eigenvectors. Still, we haven't discussed what's the use of that. It's just I defined the concept of eigenvalues and eigenvectors. Here, just I'm explaining to you how to compute eigenvalues and eigenvectors. So we will learn later what's the use of that. Okay? Let's just think about it. A is m by m matrix, right? Then we try to compute A minus lambda I, whatever, determinant. When you compute it, this becomes polynomial, right? You know what polynomial means, right? 다항식? I don't know how. Like this is basically, whatever lambda n. So this is more or less polynomial. Its dimension is n. Do you agree with that, 정민영? Is this n by m? It's 2 by 2 matrix. This is 2차 방정 형식, right? When you have 3 by 3, 이연경. This is 3차, right? Because a minus lambda with diagonals lambda. Then when you multiply that, then multiply diagonals becomes whatever. Minus lambda, this term is always there, right? So when you have like 10 by 10, this equation with whatever is lambda 10 will appear there. So you have to solve them. Even how do you solve them? In the case of 2 dimension, it's fine, right? Even in the case of 3 dimension, anybody is remember or memorize how to solve like whatever, like a x3 plus bx2 cx plus d equals 0. We learned about, okay, closed form solution exists, but nobody remember, right? In the case to the second order, even we know that, right? So beyond third order, you may have to use numerical method. Okay? So once you compute that, then you are able to find these eigenvectors. So any question up to now? Then for a simple small size of matrix, we have some properties. Let's say this is a 2 by 2 matrix. Okay? This 2 by 2 matrix. We're into the concept of trace. Okay? Trace of A. A is matrix, square matrix, right? Trace is sum of diagonal entries. So what's the trace of this A? 이영경, what's the trace of sum of diagonals? 0 plus 0. Okay, that's trace. Okay? So sum of lambda I is actually equal to trace for any matrix. Okay? Then let's think about this. What's lambda? So anybody can guess without computing? What's possible lambda? Because this 2 by 2, right? We need 2 lambdas, right? Can you guess? Using property, lambda 1 plus lambda 2 should be 7, right? 1 plus 6, right? Okay, so lambda 1 plus lambda 2 is 6, or 7. From this matrix, can you guess one, just, lambda easily? 김상우, can you come with one lambda? Because this is matrix singular, right? Means lambda equal 0 should be at least one of the eigenvalues. Then then lambda 1 is 0, then the sum of them is 7. So lambda 2 should be 7, right? Okay? Yeah, so trace is the sum of these diagonal entries. Okay, trace is sum of the diagonal entries. No, you don't have to be symmetric. Just diagonal. This is not symmetric, right? So sum of these. Okay. So we learned 2 properties. One of them is, sum of these diagonal entries we call trace is the sum of eigenvalues. Also, in case matrix A is singular, then lambda equals 0 is the one of the eigenvalue. So using that property, in many cases you can simply compute them, right? Okay. So another property here is, let's move on to previous matrix. from previous example, right? This is in the case of this permutation matrix. We computed two eigen vectors. Do you notice any property between this first x and second x? Like one of them is minus 1, 1, second one is 1, 1. So anybody can notice any properties between any relationships between two vectors? So for n by n matrix, so how many eigenvalues? When you try to compute A minus lambda I, right? The determinant, right? This is nth order equation, right? So it means we have n eigenvalues, right? But sometimes some eigenvalues are repeated. Let's think about this one. Let's say this is, let's say 3 by 3. What's the eigenvalues of this one? This identity matrix. What's the eigenvalues? That this is basically 1 minus lambda, 1 minus lambda, 1 minus lambda, then this is the one, right? 박창호, right? Then what's this? The eigenvalue is 1, right? So basically lambda is actually 0. Oh, this is 1 and 1 and 1. Okay? Another question I'm going to ask you to 현상 1. Is eigenvalues always real or it may become complex numbers? real 실수 or 복소수? Always. This is nth order equation, right? Even second order equation, sometimes you try to solve, sometimes you have whatever this within root, this number might be negative, right? Can you understand it? Because for second order equation, whatever we just call them, let's say we can, okay, A, B, C, D. Then based on that, now, okay, I'm going to compute whatever lambda. It means A minus lambda, B, C, okay, D minus lambda, right? This second order equation, right? Then I say this is 0, right? What's this? This is lambda square, right? Lambda plus AD minus BC, right? This is determinant, right? Then A plus D, whatever, like when you have like A square, whatever B, C square BX plus C equals 0, when you B minus 4AC, if this is negative, then you have solution of this has complex numbers, right? So when you think about it, actually, the solution for these eigenvalues might be complex. Okay? Can you come up with such cases, very simple cases? Let's think about it. Let's try this one. Okay? This is 0, 1, minus 1, 0, right? So we try to compute eigenvalues. Then this minus lambda, 1, minus 1. What's this? This is lambda square plus 1, right? This is 0, right? So what's lambda? So lambda is plus I or minus I, right? Very strange, right? Right? Very strange. It's very strange, right? Okay? So anyway, for n by n matrix, we are able to compute n eigenvalues. But some eigenvalues may be repeated. It means like in the case of 1, 1, 0, 0, this one is actually lambda is 1 and this second is 1. Basically, this one is square, right? 뭐라 그래? 이게 뭐 2중? 그죠? This is lambda 1. Lambda is 1 is just repeated values, right? Or sometimes it has these complex numbers. Okay? Previous example for this one, okay, we have two distinct lambda. One is economic minus 1. For each case, we were able to find orthogonal vectors. Okay, sometimes we are not able to find orthogonal vectors enough, especially the matrix singular. Okay? So I just explained using examples. This is a summary of how to compute these eigenvalues and eigenvectors. Basically, you just rewrite the equation to a minus lambda I x. That a minus lambda I should be singular for eigenvalue, right? That means determinant should be 0. Okay? So based on that, so we call this one as, we call them as characteristic equation or characteristic polynomial. Okay, basically it's a determinant of a minus lambda I. So based on that, when you formulate them, it will be a polynomial of order of n, in the case of n by n matrix, right? Then we solve them, then we can find all values of lambda. Sometimes lambda has some repeated values. Okay? So in the case of identity, lambda is 1, right? 4 by 4 is lambda 1, 1, 1, 1, right? Sometimes order of distinct, sometimes repeated. Or sometimes it has some complex numbers. Okay? Then for each lambda, we solve the equation. Then we will find eigenvectors. Let's have an example here. This matrix 3, 1, 1, 3. Okay? Here determinant, right? Then we can compute it this way, right? Then based on that, what's the value of lambda? Lambda 4 and 2, right? Then you can verify, is it correct? Then when you add 4 and 2 is 6. Trace is sum of diagonal 6, right? Or seems to be correct, right? Okay? Okay, another property. When you have a trace, like a sigma of lambda, I say this is equal to trace. Okay, this is one of property of lambda. The other one is, what about this is product of lambda, right? You know this symbol, right? Like lambda 1 times lambda 2 times whatever lambda n. This is a determinant of this matrix. Okay? So sometimes actually using this formula, you can find them. Okay. Then for each lambda, you try to compute eigenvectors. Oh, can you come up with this easily? Or so how can you compute this? Let's say, in this case, lambda 1 is 4. So you try to compute what vector x is eigenvector. So how can you compute? Let's say this is total procedure, right? So up to now, we try to compute all eigenvalues, right? But for each eigenvalue, we try to find eigenvector. Okay? So how can you find eigenvector? Basically, let's say so lambda is 4. Is eigenvalue. The specific example. So how can you find the eigenvector? This one. I just come up with, magically I just come up with, okay, this one is by whatever observation. But can you somehow, so how can you come up with that? What's this? Basically, this one is means AX, right? And this lambda 4, right? Should it be 4x, right? This relationship, right? Basically, you try to solve this one. This is for two-dimensional, right? It means what was the original matrix A? 3, 1, 1, 3, right? Right? Just by solving this is a 2 by 2 equation, right? By solving that, actually, you can compute x1 and x2, right? Kim Sang, can you follow this? So sometimes just purely by observing that you can find them, right? Here is, I just choose x1 is, here is x1 is, let's say, 1 and 1. But when you multiply, whatever, 2 is also is okay, right? So it basically means when you multiply constant here, there's also eigenvector, right? Okay? So that's the way you can compute. Then also here, in the case lambda 4 and then lambda 2, because they have different lambda, all these eigenvectors we found are orthogonal. Okay? In last lecture, I explained what's the use of orthogonality. When your base vectors are orthogonal, means when you multiply vectors, it's much easier, right? That's why orthogonality is important. Okay? Okay, there is 2 examples. First one is matrix 0, 1, 0, 1. When you compute eigenvalues and eigenvectors, so these are the result. So another matrix 1, 3, 1, and 1, 3. Then eigenvalues and eigenvectors. Can you notice some tendency or behavior here between 2? 이영경? This is 1, this is, so somehow can you some behavior? What's the matrix A1, A2? In a way, it's A2 is, let's say, A1 right? So when you add 3 times sort of identity matrix, this become A2, right? 박한솔, right? Then in that case, okay, eigenvalues, when it was 0, -1, now somehow 4, 2, right? So eigenvalues was added by 3. 박창호, right? 예? Lambda 1 should be, okay, this one should be 1, okay, you're right. This one should be 1, right? Yeah, sorry. So basically they are same eigenvalues, eigenvectors, but eigenvalues are shifted, right? So anybody can explain why? Here actually, I'm asking your intuition, 직관. This is very, very important when you somehow, because that's why I just show you several examples, then ask your intuition. Okay? So just based on this observation, seems to be 3 is shifted, same eigenvectors, somehow these lambda values are shifted, right? Then when I say 5, 1, 5, 1, then might be this, and then now it's 6 and 4, right? So that's the somehow guess you can make. Okay? Then you have to say why. Basically, this equation simply show that. So A2 is okay, A1 plus 3i. So basically, so that's the reason. Very simple, right? So when you add identity matrix to whatever matrix, then eigenvalues will be shifted, but eigenvectors should be the same. Okay? Okay, so vector A, matrix A, then eigenvalues whatever lambda. Then vector B is eigenvalues beta. How about A plus B? Why? Okay, seems to adding both parts should work, right? Okay, this relation hold for A's eigenvectors only. Okay? This relation hold for B's eigenvectors, right? So when there's no way, when you add up, it doesn't make sense. Because A's eigenvectors might be different from B's eigenvectors. So can you follow me? Okay, that's why it doesn't work. Oh, yeah, basically. Okay? Yeah. That's okay. That's why it's shifted, right? Like lambda, whatever I, right? That's shifted. So in that case, we just added, right? So in case same eigenvectors, yes. Otherwise, no.
아까 저기에서 그 x 그 뭐지? ax 있는 부분의 x랑 bx 있는 부분의 x의 값이 둘이 같으면 저기 성립.
그렇지. 그게 이제 그 경우가 그랬으면 그 경우가 아까 우리가 이제 예를 들면은 0, 1, 1, 0. It was 3, 1, whatever, 1, 3, right? So this is case because this one is somehow shifted. Basically, this one is okay, 0, 1, 1, 0, plus 3, just identity matrix. In that case, it's shifted. Yes, same eigenvectors. In that case, hold. In general, that's not the case, right? Okay. This is another example of the rotation matrix. You know what the rotation is, right? When you have vector here, you just rotate by this, right? So when you rotate by theta, that's a form. When you rotate by 90, this is the one. So one way to compute is, yes, we can just compute this equation. Another one is actually trace is a sum of, okay, I explained lambda 1 plus lambda 2 is trace A, which is 0, right? Also, when you multiply all these lambdas, there's a determinant. What's the determinant of A? It's 1, right? So from 2, then we can easily compute them. So unfortunately, lambda is I. Okay? Especially when you have complex numbers, usually its conjugate is also the eigen value. 잠깐만 스탑하고 제가 좀 썸머를 해볼게요. 우선 아이겐 밸류하고 아이겐 벡터라는 거는 이게 이제 뒤에 굉장히 그 특별한 용도가 있는데, A라는 매트릭스가 있잖아요, 그죠? 그래서 A라는 게다 X를 곱하면 뭔가 결과가 이렇게 Y가 나오잖아요, 그죠? 예? 나오잖아요. 그 A가 X가 나오면 사실 이 방향하고 밸류가 달라지잖아요. 이것도 벡터잖아요, 그죠? 이렇게 가리키는 거 아니에요, 그죠? 그랬더니 여기다 A라는 걸 딱 어플라이 했더니 결과는 이렇게 나올 수 있는 거지, 그지? Y가 어떤 방향으로 갈지, 어떻게 될지. 사실은 이거는 그러니까 벡터가 이렇게 변하는 거잖아요, 그죠? 인풋 벡터, 이게 아웃풋 벡터잖아요, 그죠? 그래서 매트릭스 멀티플리케이션을 보면은 인풋 벡터에다가 매트릭스를 곱했더니 아웃풋 벡터가 나오는 거라고, 그죠? 이행이 그렇죠, 그죠? 이건 X고 B잖아요, 그죠? 근데 여기서 n by n 매트릭스 아니에요, 그죠? n by n 매트릭스면 요거의 디멘전하고 요 디멘전이 같지, 그죠? 같은데 어떤 특정한 벡터인 경우 요걸 멀티플라이 했더니 방향이 그것도 이상하게 같이 나오더라는 얘기예요. 어떤 특정한 것. 근데 길이는 달라질 수 있고요. 때에 따라서는 길이가 거꾸로 갈 수도 있고, 그렇잖아요, 그죠? 어떨 때는 이렇게 많이 갈 수도 있고, 어떨 때 같을 수도 있고, 어떤 특정한 것. 그게 뭐를 의미하냐면 그런 것들이 존재하더라고요. 그죠? 어떻게 써먹을까 나중에 얘기고. 예? 그래서 그걸 갖다 우리가 그때 요거 스케일링 팩터. 스케일링 팩터가 우리가 아이겐 밸류라고 부르고, 요거를 만족시키는 그러한 벡터를 아이겐 벡터라고 불러요. 근데 이 아이겐 벡터가 만약에 람다가 1일 때 구하는 거하고 람다가 2일 때 구하는 거하고 벡터가 달라요. 예? 다른데 특히 이 값이 다르면 그 벡터들 사이의 관계는 올소곤하래요. 예? 쉽게 증명할 수 있거든요. 그래서 그게 지금 여기서 있는 거고, 이런 걸 하기 위해서 지금까지 이제 어떻게 컴퓨터하는 건 인 제너럴 아이겐 밸류 구하는 거는 그냥 A-람다 I 그래서 디터미넌트에서 제로수 구할 수 있는데, 이게 어떤 특정 프로퍼티가 있기 때문에 그거를 활용하면 쉽게 구할 수 있다는 거거든요. 그 중에 하나가 트레이스, 다 이걸 전부 더하면은 그거는 아이겐밸류의 썸이다. 는 거 하고, 디터미넌트는 아이겐밸류 곱이다. 그걸 활용하면 경우에 따라서 굉장히 쉽게 구할 수 있다는 거거든요. 실제 이걸 풀지 않고, 특히 그다음에 싱글러 매트릭스는 람다 이걸 제로가 항상 그 아이겐밸류다, 그죠? 그럼 2x2 매트릭스는 무조건 그냥 람다 제로가 들어가잖아요. 싱글러 매트릭스인 경우, 그죠? 그 나머지 트레이스 썸하면은 그 세컨 람다가 되겠지, 그죠? 예를 들면은. 그래서 경우에 따라서 그런 프로퍼티를 써서 쉽게 구할 수 있다. 이제 그게 이제 지금까지 제가 그 설명한 내용이에요. 혹시 여기 질문 있어요? Okay, then let's move on to some special metrics. In the case of a symmetric matrix, like as I said, like A transpose is same to A, right? In this case, we have only just real eigenvalues. The antisymmetric, we have imaginary. Also, in the case of triangular matrix, then in a triangular matrix, these are all lambdas. You already computed. Okay, because when you apply this whatever this u minus lambda I, then that's the equation. So that's equal to 0. Then each of these value is eigenvalue. Okay? What does this means? Let's think about it. Okay. Okay, this is another case. This A is 3, 1, and 0, 3, so we call determinant. Then lambda we found all 3. Okay? So in this case, I try to find eigenvector. Okay? Then I found one eigenvector, but there is no, I cannot find another eigenvector anymore in this case. So and then lambda i's are distinct, then we are able to find all these eigenvectors. But sometimes, lambda I is, let's say, 0, 0, 0, or you may say whatever is repeated values, let's say 3, and 3, and 3, and 3. You might not be able to find 4 of them. You may be able to find only 1 or 2 or whatever. What's the identity matrix? Let's say 4. What's the eigenvalues for this? Lambda equal 1, right? This is basically 1 minus lambda 4, right? The lambda is 1 and 1 and 1 and 1. Can you find any eigenvector for this? 김상우? This is identity matrix, right? The identity matrix, then X is X, right? It means any vector. Okay, it is any vectors there, right? Okay. Sometimes you cannot find more than 1. When I say 1, it means independent. Okay? So in this specific example, we can find the first eigenvector, but I try to find second eigenvector. I'm not able to find them. Okay? Actually, this is proof. When all eigenvectors are different, then all these eigenvectors are, say, here is, I say independent. 바꿔진, I made a mistake, just it's independent, not orthogonal, okay? Okay, so certain cases is orthogonal. Okay, this is just independent. So when you have eigenvector 1, eigenvector 2 should be independent. But in some specific cases, there's orthogonal, okay? So this is proof. 제가 강의는 여기까지 끝낼게요. 그래서 지금 오늘 아이겐벡터라는 얘기를 쭉 했는데 이제 한번 이렇게 해봅시다. 여러분 캘큘러스 배웠죠? 예? 그 다음에 테일러 시리즈 익스펜션 배웠죠? 예? 그러면 예를 들면은 이거 물어봅시다. 이거 어떻게 계산해요? 이거 테일러 시리즈 익스펜션은 어떻게 돼? 이렇게 쭉 가는 거 아닌가? 이게 보면 이게 수렴이라고 그러나? 어떤 조건에서 수렴을 해요? 예? 이거 적을 때죠, 그죠? 마치 한번 이렇게 써보죠. 이렇게 우리가 이렇게 쭉 가는 경우도 있거든요. 대칭 내용이 요거예요. 어떤 경우에 이 값이 수렴을 할까? 수렴을 한다는 얘기가 뭐예요? 이 뒤에 가면 같이 이게 제로라는 거잖아요, 그죠? 뒤에 값이 제로라는 거잖아요, 그죠? 그래서 수렴하는 거잖아. 그렇지 않나? 근데 벡터로 계속 멀티플라이 자기를 했더니 그게 전부 제로로 갈 수가 있거든요. 그러니까 제로로 수렴한다 이게. 이제 그런 컨셉에 이게 쓰일 거예요. 이게 대강 어디 쓸까 가지고 궁금하기 때문에 그런 컨셉에 쓰일 거라고. 물어봅시다. 그 점화식이라 그러나? 리커런스 이퀘이션, 디퍼런스 이퀘이션 배웠어요? 고등학교 때 뭐 시험 난 것 같은데 옛날에 보니까. 점화식이 뭐예요? 아니 물어봅시다. 뭐 뭐죠? 슈노바치 남바인가? 예? 예, 그 남바가 이제 뭐 1, 그다음에 뭐예요? 2, 그다음에 3, 5 이렇게 가잖아요, 그죠? 그러면 이 남바가 예를 들면은 요거의 100번째 건 어떻게 구해요? 어프로시메이트리. 이런 거 저기 그 어디야? 거기 디스크리트 매스에서 안 했어요 아직? 예? 했어요? 그래서 거기서 뭔가 이걸 구하는 방법이 있죠, 그죠? 예? 그러면 왜 이때는 이게 구해지고 어떤 이런 아니면 이게 가면 이렇게 계속 가잖아, 그죠? 어떤 경우는 이게 제로로 가잖아, 그죠? 그죠? 이건 수렴을 안 한 거잖아요, 그죠? 그러면 이게 어떤 팩터로 이게 증가하고 있나? 이제 이런 것들을 푸는데 이걸 살 거예요. 무슨 얘기인지 알겠죠? 예? 현재 그런 용도에 쓸 거예요. 오케이. 그렇게까지 얘기하고 질문 있어요? 그래서 다음에는 이 개념을 얘기하고 그런 그 디퍼런스 이퀘이션을 몇 개 예를 들어서 그 익잠플을 해서 이런 경우에 이 값이 어떻게 수렴된다 아니다 이런 얘기를 할 거예요. 자, 오늘 수업 이거 끝냅시다.